Let's take a look at what this one, the data acquisition, means on the PSoC designer, and then also I updated the suppress application note for the using A to D converters. So there's application note about accurate measurement using PSoC3 or PSoC5LB delta sigma ADCs. So you might want to take a look at that one to get some hints how to actually configure the A to D for good accurate results. Otherwise, we actually, let's take a look at the what this exercise is all about. So in this exercise you will need only this prototyping board and then analog sensor, and actually you will start with a old-fashioned potentiometer. So basically you would be doing an oversampling A to D converter, downsample the data and send the data to the computer. So basically on hardware side, for the testing purpose you would just have a potentiometer like that one, so in terminal 1 and 3 between ground and the operating voltage, and then this slide should be connected to the input port of this PSoC device, which then actually have the A to D converter there running. On software side you would have a downsampling software that you will be practically actually writing yourself, and then this application also uses the USB UART bridge on the KitProc, and you will communicate with this device on with a terminal program. Okay, let's see. First things first. So what you would be doing, create a new project using example CE195277 ADC and UART, and rename it. Okay, let me take that name here just for fun, copy paste, and then connect the potentiometer so that you can vary test signal between 0 and VCC, and basically that should be connected to port 0.0. But let's take a look at the program PSoC designer here. So we start with the create new project and create from code example, and here actually you can try to find the ADC kind of, okay, there's that it's this one. So it should actually show that this is for the PSoC5LP prototyping kit. Click, maybe change the name and also the project name here, put it on your favorite directory. There, finish it up, and the design actually shows already that it has a, well, this is an excellent example how to actually document your this design, top design. So remember, this is not just tool to create things, but it's also tool to document it at the same time. So this is an example of how all of these designs should be documented on the first place. So it has just two components. One is the delta sigma A to D converter, another one is UART, and there's also instructions how to test it, including the how to actually what kind of commands you would be sending from the terminal program and what you should get as an answer. And by the way, you also got probably at the middle on the beginning you got this the documentation opening up on your window. So okay, that actually shows you what you should be doing. Hardware setup, that kind of stuff. Okay, let me close that. All right, and I told you something about the pins. So the input should be at, yes, connect positive terminal of DC to a voltage source using port 0.0, and otherwise this is just plug, program, connect, and then find your port on the computer, open the terminal, and that should actually give you access to the system. Okay, I believe that one. So what I will be doing, just clicking build. Build actually starts from the beginning, which means that first thing is that it checks if this one requires generation of the APIs, and then it has now it's still there on the output window showing stuff. Okay, build succeeded. Then we can actually go to the program. Oops, well, yeah, it may actually help if I power it up. Okay, now I have it. So I didn't have the board connected yet. Now it should be actually running. Okay, so let me show you first my connections. Here's the pot, and again I'm using the extension wires, and then I have a nice slide that I can actually then select the voltage. Okay, down here there are terminal pins 1, 2 and 3. This one actually shows quite well that in between 1 and 3 you have that blackish stripe here. That's the variable resistor, and pin 2 is the middle pin. That actually, if you look inside, it's a metal that connects this slide, this resistor varying here. It connects to that terminal. Okay, so very simple slider connector. And next I would like to know which port I'm using, since I've changed actually something on here. So device manager, okay, ports COM4. So I have plugged in this system into COM4 with the parameters bitrate 115/200. So I need to do some changes on my terminal. Where do we need? I will cancel that one. I think this is on the wrong speed. So okay, yeah. Oh, I had the director serial COM4 and the bitrate was 115200. Let's check that it is actually like that. Yes, 115200. Open. Okay, there I have. I will then reset this one just for fun. Comport open, and then these commands are C actually should send. Yes, when I press C, it actually gives me sample and how many millivolts, and then see continuously transmit starts with S. And proving that it works goes to, well, 0. Okay, why it goes to these negative values? Actually, that's a one feature of this sigma delta A to D in PSoC. It's not rail to rail. So when you go down to 0, it gives you faulty answers. So this is totally bogus. But then when you are within some range, I think it was it 100 millivolts or something like that, above 100 millivolts. No, actually, let's see. It goes down to 20 millivolts, and then basically after 20 millivolts, it's too small. And same thing when you go up here, 2.3, 2.4. Okay, 3 volts, 4 volts on. Okay, I wouldn't be trusting those voltages actually here. So I think it was something like 0.2 volts before. Oh, yeah, actually this could be. So I'm not getting the full VCC from this potentiometer. That's nice. Okay, so it works. All right, so let's stop and then sample. Yes, oops, stop. Good. So the design, that example design actually works as expected. Okay, so next what you should be doing is to connect the analog temperature sensor. Analog temperature sensor LM35, which is somewhere in here in my box. Okay, it looks like this. Let's open the camera again. It practically looks like this. Small device. Okay, some advice now. This is very sensitive device. So when you are connecting it, well, that will be just the signal source. But observe the pin out. Reversing the polarity of this device will destroy it. No, that's guaranteed. It will die immediately in a touch. So go and check what this data sheet is actually giving you, and especially the okay, here the pin out. No brainer. This is this package 1, 2, 3 plus VS, V out, ground. Okay, this is bottom view. This is old-fashioned transistor package, TO92 package. There the pin out is almost always given from the bottom side. compared to these, say, integrated circuits packages, modern packages, it's a top view. So observe this one, bottom view. Don't burn it. If you are not sure of it, take a break, take it a look at the device again, and then do the connections. This might be the only sensor of this type in your package, and basically you want to really want to test the system with the real sensor in order to see if it's working or not. Okay, so now you have been warned. Okay, so the first thing actually would be just to test if you can read that value now. Okay, that's actually 10 millivolts per centigrade. So in principle you should get something between 200 millivolts to 250 millivolts reading from the device. You are probably making this in room temperature. So that's about 20 to 20 C. So with that conversion rate of 10 millivolts for centigrade, actually you will get 200 to 200 millivolts reading. Okay, then you should actually make the A to D converter to run somewhere, say, pretty fast, 1,000 samples or up to 10,000 samples per second. What is the exact sampling rate? It's not critical for this exercise, since you will be doing boxcar averaging, meaning that actually, as in this picture, you take half second time frame, you average all the A to D conversion values, or actually you calculate the running sum and divide it by how many samples you have on the sum. Use long enough variables to save the data. With 1,000 samples of 16-bit data, for example, you need more bits. Okay, and this value, time average value, is something that will be then used on the transmitting it. Okay, so yeah, you need a mechanism to calculate the running sum. I advise you to use global variables, meaning that actually on the code, let's go to the main, you have defined somewhere defined a for example 32-bit unsigned integer sum, make it 0, maybe uint 32 count, that also starts from 0. Then on your interrupt service code, yeah, I don't know where do I have the interrupt. Oh, okay, there is one, for example, wart interrupt, or actually let's say delta sigma interrupt. I think that probably has the interrupt, A to D interrupt on here. If you're using the this ADC interrupt routine, then basically you need to define these variables sum and those count there. You need to define them here. Define these as external variables, then they basically are pointing to the same variable as in this main.c source file. Okay. And same thing if you want to have some flags to show that to tell to the main routine, okay, now the conversion is ready, the sum is ready to calculation. Another detail here, when you are calculating the average, there is a chance that you will get more data. So during the calculus, the values might actually change. So you might be actually, for example, dividing the sum with number which was updated or the other way around. So they wouldn't match. So disable the interrupts during calculation of the average. Okay, otherwise the sum of those may actually change due to occurring interrupts. Okay, convert. Then you need to convert the HDC values to corresponding temperature within 0.1 degrees Celsius accuracy. So I would like to see there 24.1 degrees Celsius, for example, on the screen. When you have actually got that one on your terminal, then you at the end basically, okay, go and make that message to JSON format, which is right there actually, or go to the json.org to see what kind of data script you would be getting. Okay, and then of course after testing that the design works as required, save this one. You will need it as the basis for the next exercise. Okay, so that's the deal for the exercise 3. And exercise 3 return is on April 30 at the end of the day.